Hi, and welcome to my presentation, Prediction of Human Full Body Movements with Motion Optimization and Recurrent Neural Networks. Planning robot motion in close proximity to humans is challenging, as we do not want to disturb the human's natural motion flow or even collide with the human. We believe that the key ability for safe and efficient human-robot interaction is to predict the human behavior. In this work, we propose a novel full-body motion prediction framework that can adapt to the environmental context. We show how this could be used for human-aware planning of robot motion. This image shows several frames of a human trajectory reaching towards a cup on a small shelf. We define the motion prediction problem as follows. First, we observe an initial trajectory of human motion to some time step t, here depicted in blue. Second, we want to predict the following states of the human, here depicted in green. It is clear to see that a good prediction would respect both the human internal dynamics and the environment. Related work achieves good results on learning short-term motion prediction using recurrent neural network architectures. For example, this video shows some ground truth trajectory of walking motion depicted in gray and a RNN-based prediction in red. It can be seen that the prediction is initially very close to the ground truth, but then diverges because the prediction tends to walk into a different direction. However, one can observe that it still looks like typical human walking motion. An issue with these approaches is that they only forecast pure human motion and do not adapt to the environmental context. Incorporating environmental context directly into the architecture is hard. One would need a way that generalizes well over the enormous amount of different types of environments and the enormous amount of interaction possibilities. Also, one would need to capture large amounts of training data. Trajectory optimization algorithms are widely used in robotics. One advantage of these techniques is that they can successfully generate motions with a variety of kinematic and dynamic objectives. For example, jump allows motion planning with non-convex obstacles. Our approach combines the two fields. It works as follows. Offline, we train a state-of-the-art RNN architecture on human full-body motion. Online, the model can be used to predict a trajectory. However, this trajectory is only based on pure human data. We extract constraints such as goal set or collision avoidance from the environment. Furthermore, we add additional parameters delta to the RNN model, which allow us to use numerical optimization techniques during the prediction phase in order to adapt to the environmental constraints on the fly. We base the architecture for prediction of the internal human dynamics on the position velocity encoder-decoder model by Wang and Feng. In our case, a single RNN cell stacks multiple shear rule layers and a linear layer. The input to the cell are the base rotation, the joint angles and velocities. The output of the cells are predictions of the next velocities. By using a residual connection, which adds the velocities to the initial state, the next state can be predicted. After time step t, we can loop the predicted velocities and states into the RNN cell to predict multiple steps into the future. As the inputs are predictions, they slightly deviate from the real state of the human. The small errors accumulate so that the prediction could end up in a completely different end state. Finally, we add the controls delta to the velocity input in the prediction steps. This allows us to change the prediction of the network at each time step. Using information from the environment, this can help us to compensate the small prediction errors mentioned before. In the numerical optimization step, we use the objective shown here. The low level is used to keep the control parameter small, so that the inputs to the network stay close to the original inputs. The goal set objective penalizes the distance of an end effector, such as the hand, to a goal position. it can be used to predict motion towards an object. In order to avoid collisions with obstacles, we use an obstacle potential, similar to the one used in jump. Our framework also allows to jointly optimize for a robot and a human trajectory at the same time. While prior work often treats the human prediction as a black box, this is not true in practice, as the robot motion also will influence the human behavior. Using a joint objective allows for a bidirectional information flow between human and robot. For example, the objective shown here penalizes close distance of the human position P to the robot position X, which avoids that human and robot collide. For the robot, additional objectives, such as a smoothness objective or obstacle and goal objective similar to that shown on the previous slide, can be added as well. To optimize the objectives, we obtain a final loss function by summing the weighted costs. We compute gradients using automatic differentiation frameworks and use the limited memory BFGS algorithm to optimize the final costs and find the optimal parameters for human and robot. For our experiments, we captured 120 minutes of full body motion data using a motion capture system shown here. We trained the ERNN model on a part of the data and hold some data back for testing. The data includes walking and pick-and-place motion. The human is represented using a kinematic model. For the experiments, we use 1 second of ground truth motion and predict 1 to 4 seconds of subsequent motion depending on the experiment. This slide shows an example walking trajectory. The green prediction is optimized using the goal objective with an oracle goal. The red prediction shows the initial prediction. It can be seen that the prediction with goal objective is very close to the ground truth, while the prediction without the objective leads to a different end location. Here we show reaching motion with the goal objective. The left side shows the ground truth, the right side the prediction. It can be seen that the prediction is very close to the ground truth. In this video, the prediction with a naive model, shown on the left side, collides with the chair. Adding the obstacle objectives solves this issue and leads to an overall better prediction. Here we can see the average performance over 22 reaching trajectories of 2 seconds. The distance error on several time steps is shown. It can be seen that in the very beginning the methods lead to a similar error. When using our proposed method with an oracle goal location, we can improve the initial prediction. The method using both goal and obstacle objectives performs best. This video shows a preliminary experiment for the joint objective. The human and the robot are optimized to end up on specified positions. On the left side, we show the prediction without objective. The human and the robot collide. On the right side, we show the predicted trajectories when using the joint objective. Both the human and the robot deviate from their initial prediction so that no collision happens. In this work, we presented a novel prediction method for full body motion. Our framework makes it possible to adapt the prediction to environmental context, and we demonstrate the approach on experiments with real human motion data. Furthermore, the framework allows for combined human and robot trajectory optimization, which can be used to plan robot motion while predicting the human at the same time. One limitation of the framework is the high computational cost of the network input-output Jacobian. Future work involves more compact modeling of this Jacobian. Furthermore, it would be possible to connect our framework to the concepts of affordances. Knowledge over the object affordances can be useful to extract good goal set constraints for the optimizer. Thank you for your attention.